Uh, Hello, everyone. Thanks to the organizers for giving me this opportunity to present this work. And this is a work which was jointly done with many of the ex-postdocs from ICTS, Jwel, like Siddharth, Vishal, and so on, and the student, Akhil from ICTS, and Mukund, Julio, and Temple. These three people are from UC Davis. And the work that I'm describing here has been written up in these three archive numbers, and also I'll also be making reference to some of the ongoing work. Okay, so let me basically start with some motivation. So the basic idea which is driving all these things and which we want to understand in these works is that is there's a deep relation between two very interesting physical systems and physical ideas. One is, if you consider, let's say, a fluid, some kind of a hot plasma, it could be a strongly coupled plasma, which in our case, which is described by some kind of hydrodynamics, and you look at the energy fluctuations in this plasma. Okay, so it is described by some kind of fluctuating hydrodynamics, which presumably controls this energy fluctuation. So that's a kind of one class of very interesting systems. And on the other side, you can think about some seemingly completely different system, which is, you think about a black hole, okay, which is a solution of the Einstein equations, and it is and the Einstein equations also have gravitational wave solutions. And one of the things about black holes that Hawking has told us is that the black holes also radiate. Okay, they radiate in particular also gravitational waves. So there are some, random gravitational waves which are emitted by even by a black hole which is at rest, which you can think of as some kind of analogous system. You can call it fluctuating gravity. Okay, if you want, in analogy with this fluctuating hydrodynamics. And the statement is that there seems to be some very deep analogy or relation between these two systems. So one way to understand that why we expect there to be this relation is in the context of ADS-CFT, okay, or string theory, okay, which I won't go into, but the statement, I think, is perhaps more general, and this makes it very interesting. Now, of course, each of these problems themselves are interesting. They are intrinsically very interesting and challenging questions of how to think about them and how to characterize them quantitatively and so on. But the fact that these two are related and one can talk about both of these very challenging questions together makes them more fascinating. Okay, so this is a kind of a broader motivation to try to understand how this works, okay, within ADS-CFT and probably more generally. And this is what kind of motivated us, some few years ago, 1 or 2 years ago, to kind of start studying these relations in a detailed quantitative way. And what I'm trying to tell you guys is what we have found, okay, and what we think, how we think this thing works, okay. So that's a basic motivation. Okay. So let's kind of get somewhat deeper. Okay, so let me start with saying some things which are somewhat obvious statements, but I think it's worth recalling. Okay, so when we talk about something like fluid dynamics or hydrodynamics of a system, what we are thinking about is that usually there are some microscopic degrees of freedom. Okay, some short distance, short-lived microscopic degrees of freedom. Let's say water molecules in water or something, whatever the underlying molecular atomic structure, or if you're talking about something like quark-gluon plasma, whatever are the constituents of the quark-gluon plasma, and so on and so forth, right? There are some short distance, short-lived microscopic modes which we want to integrate out, okay, and kind of write down some effective theory of this long-lived, long-distance modes, which is what we call as hydrodynamic modes. Okay, and often these hydrodynamic modes are modes which are associated with conserved charges. Okay, which are their energy, they are associated energy transport, some number transport, or some other conserved charge transport, and so on and so forth. Okay, and we think that like in a generic system, if you have a finite temperature, dense enough systems, then like there'll be some kind of hydrodynamics which will describe these long distance modes. Okay, so the question, there's something more one can say. Okay, so this is something that we often say, but there's also something more which is also true. Okay, that if you think about fluctuations in such a kind of system in hydrodynamics, okay, and there should be fluctuations because all hydrodynamics are thermal systems, they're statistical mechanical systems, and there are always some fluctuations in such systems. These fluctuations also have this kind of a distinction, that in a certain sense there are like long distance, long lived fluctuations, which you can call as hydrodynamic fluctuations, as opposed to short distance, short lived microscopic fluctuations. Okay, it's like I don't know how to kind of define this very precisely. Okay, apart from the saying that like we have to kind of the microscopic fluctuations are the ones which are short lived, and the macroscopic fluctuations are the ones which are long lived. Okay, but like when we think about something like fluctuating hydrodynamics, what we are trying to say is that we want to integrate out these microscopic short-lived fluctuations and keep the macroscopic long-lived fluctuations, and then you get something like hydrodynamics with hydrodynamic fluctuations. Okay, so this is at this point like somewhat vague statement. Okay, but like but I think like this is kind of like intuitively true. One way to kind of justify the statement is that hydrodynamics describes some long-lived modes which dissipate, and we think that like a system near equilibrium, fluctuations and dissipation are very closely related, which means they should have long-lived fluctuating modes also. Okay, so that's one way to motivate why there should be long-lived fluctuating modes, which are distinct from short-lived fluctuating modes, and which we have to kind of keep and integrate out the effects of the short-lived fluctuating modes to get something like fluctuating hydrodynamics. Okay, so there are various like kind of toy models in which people have started studying these things in various contexts. Okay, but I think it is fair to say that none of us really understands how this separation works quite well. Okay, so that is regarding fluctuating hydro. Okay, so let me say like why this kind of way of thinking about fluctuating hydrodynamics. What does this have to do with gravity and black holes and gravitational waves and so on? Okay, and the basic relation which is kind of related to ADS-CFT is what is called as a fluid gravity correspondence, which is a kind of set of ideas which has been developed since 2000 by a whole set of people. I can't cite all of them, but like by many people. Okay, and the idea arises from this statement. Okay, that is, if you study a certain kind of like black holes in ADS, which is a particular kind of space-time, doesn't matter what it is. Okay, then the modes of that black hole, okay, also have this kind of a distinction of a slow hydrodynamic quasi-normal modes, okay, and fast quasi-normal modes. The quasi-normal modes are the modes which fall into the black hole, in case you don't know. And the statement is that like because of this slow fast separation, these slow modes have some effective hydrodynamic theory, and in fact like they are described by some kind of Navier-Stokes equation. Okay, so and you can kind of understand it heuristically, like what I have like shown in this slide, which is that like there are some modes which kind of hover around, like in this Newton's thought experiment, where if you kind of throw a projectile which has sufficient horizontal velocity, it kind of goes around and around for a long time before it falls. And similarly, like there are some modes which kind of hover around for a long time, and they are effectively described by some kind of long-lived hydrodynamic modes and some kind of a effective Navier-Stokes equation. Okay, and this is the statement of like fluid gravity correspondence, and the fluid gravity correspondence is basically hence a map where like you basically say that you can like if you give me some kind of fluid configuration, you can find a similar configuration of these slow quasi-normal modes around the black hole. Okay, which then evolves according to the Einstein equation, and where the when the fluid configuration evolves according to the Navier-Stokes equation. So there's a map where you can write down a metric which has just velocities of and so on, so that if the metric satisfies Einstein equation, it is equivalent to saying that those velocities that enter into the metric satisfy Navier-Stokes equation.
Loga, 5 minutes remain.
Yeah. Okay. So the statement is that we want to add fluctuations, to both these sides. Okay. To kind of, so this is the fluid gravity correspondence, which is the statement that there's a one-to-one correspondence between fluid modes and quasi-normal modes. And what we wanted to do was to add fluctuation to the both sides. Okay. So there's a fluctuating hydrodynamics, which is natural to add on the hydrodynamic side, as I said. And on the metric configuration side, adding fluctuations is equivalent to thinking about adding Hawking radiation. And as I argued for this hydro side, that there are slow, fluctuations and fast fluctuations. The corresponding statement in the case of Hawking radiation is that there are slow Hawking radiation and there are fast Hawking radiation, and it is that kind of distinction that we kind of also showed in the case of by solving Einstein equations. Okay. So this is the kind of thing that exactly what we did. So what the statement is that is to kind of separate out the slow Hawking radiation versus fast Hawking radiation. So you can in the series of works, what we showed, okay, is what I have written in bold, okay, in this slide, okay, which is that we have constructed a set of very slow fluctuating metric configurations, okay, which solve linearized Einstein equations. Sorry, that should be Einstein equations, and in these configurations we computed their actions and their corresponding conserved quantities and so on, and showed that they are what we expect out of fluctuating hydro, which means that basically in this map you can add fluctuations on both sides, where Hawking radiation is the fluctuation on the other side, and you can make sense out of it. Okay. Then I have some technical details which I don't think I have time for, so I will just skip this. Okay, to kind of just say some things about to summarize. Okay, so the statement is basically this, that that we have. So the statement is that if you have a fluctuating fluid configuration, okay, you can construct a corresponding fluctuating metric configuration, which you can think of it as basically metric, which is dressed by some kind of Hawking radiation, okay, of gravitational waves, okay, and there's a precise mathematical map we can write down, okay, between one side and other side. And the statement is that you can do that at the linearized level. That's what we have done. Okay, that is when LHS solves the linearized fluctuating hydro equations, the RHS solves the linearized fluctuating gravity equations. Okay, and there are many natural questions one can ask of how to extend, okay, this beyond what we have done, okay, beyond what we have done in these works. One natural question, the most interesting thing both in hydrodynamics and gravity, are the nonlinearities, which is to take into account nonlinearities and whether this map can be extended beyond the linearized level. Okay, so that is one very interesting question. One way you might try to address it is to kind of add in scattering of the Hawking modes and this and the modes which are falling in. Okay, so one toy model of how this might work, okay, though this has to be worked out, is kind of presented by Godwin, in a toy scalar model. So the question is to take that model and try to see we can extend it to gravity and understand the corresponding statements in the fluctuating hydro. Okay, and there's also some more general questions about these long-lived slow fluctuating modes, okay, in many other gravitational setups. And one of the things that I've been interested in is in the cosmological context, where maybe these long-lived slow fluctuating modes have a very important role to play in how let's say large-scale galactic distributions and so on and so forth in the large-scale structure and so on. Okay, and the question is to how to kind of make that precise, and whether we can kind of use fluctuating hydrodynamics and insights from there to understand these questions about large-scale structure and so on. Okay, so with that, let me conclude and thank you. Okay. Yeah.
Thanks, Loga, for the nice talk. We can take a couple of questions. So regarding the
I have a
metric
question,
perturbation
Loga.
from the
Sorry. There was one question here.
can I ask?
Yeah.
Yes.
Sorry.
Yes, Venta, maybe I'll take a question here and then I'll come back to you.
Sure.
Okay.
Sure.
So regarding the metric perturbation you have said of the Hawking radiation, so is it a scalar perturbation or vector or tensor? I mean, which part is going to be?
Yeah, so you have to actually, okay. So the statement is that, so this is part of, like what I was saying. The statement is that actually there are all these perturbations. You have to do all the perturbations. And you'll see that, like the tensor perturbations are short-lived. Okay, they don't correspond to long-lived modes. But the vector and the scalar perturbations are long-lived, and they do correspond to the hydrodynamic modes. Okay, but yeah, so part of the technical details is how to separate them out and understand, like how to deal with these slow modes and fast modes.
One more question. So is there any possibility like this gravitational waves can create the CMB polarization, E mode and B mode polarizations by distorting the space-time? So is there any possibility by Hawking radiations it can create some other polarizations of the CMB?
The CMB is, but photon has only two polarizations. No? I'm not sure.
Yeah, because there are cold, hot. So these kind of patterns are created by the space-time variation of this.
Yeah, so maybe what you're asking is that, like the gravitational wave fluctuations in the cosmological context, what do they, imply for, the CMB polarizations?
Yeah,
I think that's a very interesting question, but I don't have any answer. Okay, because the cosmological thing is something which we want to do. Okay, but I don't know, but that's a kind of question that we would like to answer. And whether there is a analogous statement with fluctuating hydro, whether we can relate it to something like that. Yeah.
Thanks.
Spenta?
Yes, Loga. I just wanted to ask this question that you mentioned that Hawking radiation may have something to do with structure formation and stuff like that. But we know that the Hawking temperature is, even for a solar mass black hole, is very, very tiny. So can you say something about that? What did you have in mind, really?
Well, I had in mind, in the cosmological context, I had in mind the de Sitter temperature, and the fluctuations are indeed small. But as you know, like in cosmology, we believe that there were very small fluctuations which were magnified over time, okay, to lead to all the structure that we see. So very small fluctuations are magnified over cosmological evolution. So like it is not completely crazy, I think. Okay, and in fact, we do think that the cosmological perturbations were seeded by quantum fluctuations, right? Okay.
Right.
So the question I'm asking is, what is the contribution of something like de Sitter horizons Hawking radiation to those fluctuations? Yeah.
Okay. Thank you.
Yes.
So normally in hydrodynamics, one way is like we get it by some coarse graining of originally microscopic theory. And then, because we had done a coarse graining, then there's something remaining, and that leads to the fluctuations for the long wavelength modes, right? Now, here, so where do these fluctuations come from? Like what is the underlying microscopic theory for the hydrodynamics? It's not the gravity, right? That was my original understanding, but it's not the gravity which the underlying microscopic.
So there are these two descriptions. Okay, on one side, like there's supposed to be some quantum field theory. On the other side, like there's supposed to be some, like full quantum gravitational theory with string theory and so on. Okay, but on both sides, we are looking at some macroscopic limit. Okay, so on the quantum field theory side, we are looking at some kind of hydro. Okay, whatever the microscopic theory is, okay, it is going to hydro. And on the string theory side, we are forgetting about all the strings and so on, and we are just looking at some gravitational Einstein equations, okay, of a big black hole, okay, and understanding how things fall in and how it Hawking radiates, okay. So on both sides, and the statement is that this is kind of a macroscopic limit on both sides, okay, of this correspondence, and it should still match, okay. But the microscopic theory itself is, the corresponding ADS-CFT statement. Okay, so on the gravitational side, the microscopic degrees of freedom, which causes fluctuations and so on and so forth, should be, like some string theoretical degrees of freedom or whatever is making the quantum gravity. Okay, but in our work we are kind of agnostic about it. But the statement is that we are working in the macroscopic limit on both sides. So assuming that this correspondence is true, the macroscopic limit on both sides should also match. Okay, and we see that it does, and that's the point. So including fluctuations, and it does, and the fluctuating part of the black holes does give you fluctuating hydro. Okay, so that's the basic message.
Yeah, thanks, Loga.